So basically what you guys just did in the worksheet is all the math that you have to do in section 32.3 on RC filtering circuits. Let's make sure I'm capturing the screen. Okay. And since you guys did all the math, I get to talk about, what those math means, right? So it's kind of fun. So let's just jump into, the circuit you just analyzed, right? Where we have some sort of voltage source, right? And we're driving this with some R and a C that's in series with each other, right? And you guys found that, well, we can write this using Kirchhoff's law. If I start off here, right, I can say that, well, the voltage is going to be equal to, I'm going to gain EMF amount of voltage. I'm going to lose whatever the voltage across a resistor is. That depends on time. When I cross this and I cross the capacitor, I'm going to lose some capacitance amount of voltage, right? And this allows me to basically write this equation where, oops, not square, right, plus VC as a function of time. Unfortunately, this is some sort of time-dependent equation, right? So depending on when the time is, right, the equations are actually different, which is, which kind of sucks. But the thing is, we both know that these are oscillating waves that has some amplitude. So in this chapter, right, instead of calling it amplitude, we call them the peak value. Okay, sorry about that. Let's just blame it on the electrical engineers, because they like to call it a peak value instead. Okay. What you guys just did, right? You actually solve for the peak values for both the resistor part, basically the peak value VR, right? Cosine of omega t, right? And also VC, capital VC, cosine of omega t, with this crazy phase shift that we have to deal with. Okay. And what that allows you to do is that, as you saw from the limiting case, as the frequency goes to 0, right, basically all of the voltage change, right, occur at the capacitor, right? The voltage drop happens at a capacitor, right? None of it happens at the resistor. But then as frequency increases to infinity, all the voltage drop happen at the resistor and not the capacitor, right? So that's the two limiting case I told you guys to take using these equations you guys derived. Okay, and let's look at what this looks like on a graph as a function of frequency. Okay, this is going to be a wonky thing because this is probably the first time you guys seen a graph as a function of frequency. Usually we plot time or space, right? But this is going to be as a function of frequency. But because, right, these VR, right, it depends on what the omega is, right? Right? So we can think about these amplitudes, peak values of the voltages as a function of this omega, right? Because there's no x, there's no t anymore, right? Okay? And this, if you plot this, this is what it'll look like, right? As this is, which one is which? This should be the resistor, right? And this one should be the capacitor, right? So just as you guys figured out, right, as the frequency goes to 0, the voltage across the resistor, so the peak value of the voltage across the resistor goes to 0, right? But as it goes to infinity, right, it doesn't go to infinity, it goes to whatever the battery source amplitude is, right? Right. Opposite happens with the capacitor, where at omega equal to 0, you have the same peak value as the alternating current source, but as you go to infinity, it actually goes to 0, right? So we didn't map this out further enough, but it does go to 0. Okay. What's really interesting is that they cross at a single point, right? Okay. This is known as the characteristic frequency, or the crossover frequency, omega c, right? Defined as, how do you define things? Right, they call it the crossover frequency. Okay. Okay. And it's going to be very important because if we were solving this complicated equation up here, I'm not going to do that in front of you because I'm going to make a mistake and spend a lot of time correcting it, right? You're going to find that this characteristic frequency is actually 1 over RC. It just turns out to be this very simple formula. Okay? And if we plug in, okay, in your homework you'll get to do this. If you plug in omega equal to 1 over RC into this formula up here, you just plug in omega equals to 1 over RC up here, you're going to find that all of the equation kind of simplifies, and basically the equation will just turn out to be EMF, right? So in your case it'll be is EMF thing divided by square root of 2. Okay, so if you look at this map up here, right, this is actually 1 over square root of 2 times EMF. Okay, and this is a special number when you're dealing with RC circuit, because that's exactly where the crossover frequency is. And that's when, basically think of it as, sometimes the voltage across the resistor is bigger, sometimes the voltage across the capacitor is bigger, but this is the point when they are the same as each other. Okay, right? And why is that important? We're going to use these things on circuits that we use every day. For example, if you are using your phone, right, and then the microphone in your phone has this thing called low pass filter in it. Okay, a low pass filter, what it does, it basically it does what it sounds like. It allows the low frequency signal to pass through. Okay, for example, my voice, right, human voice is about 20 hertz to about 20 kilohertz, but like, my voice is probably like 400 hertz on average. Okay, where a female voice might be like 450 or something like that, right? So these are actually, in electronics talk, these are very low frequency waves. Okay, and you want to put a low frequency filter on it, and that way all the noise, all the high pitched noise around here, let's say if you have like a bat squeaking or something like that, not that you would talk around bats, right? But there are other high frequency noise that you don't want to deal with, and therefore you put your signal through a low pass filter. That way it picks up your voice more and not the bats. I don't know if you've been talking to bats a lot, but that's just a weird example. But there are other high frequency noise, such as like the electricity, all this little humming noise that we hear every day. Okay, so this is a low pass circuit where what you're interested in. So remember, at low frequency, okay, let's just look at this map once again, right? At low frequency, right, we're on this side of the crossover point, right? The voltage across the capacitor is the big one. So if you want a low pass filter, right, what you want to do is actually put your signal through both R and C, but only look at the capacitor value. Okay, so this is what this circuit is supposed to do, where you have some microphone that you're picking up some voice with, right? You put it through both an R and a C to ground. Okay, but instead of measuring both of them at the same time, you're only measuring the part that has the capacitor. You're measuring only the voltage across the capacitor as a function of time, right? Which is this Vc value times cosine of omega t plus pi over 2. Okay, so let me see if I have some time to talk about some example. Yeah, so let's do a quick example real quick. Okay, so let's calculate what Vc and Vr is if the frequency of the sound is 160 hertz. Okay, and now we have this funky units between f and omega, right? Remember, f is just going to be omega over 2 pi. Okay, where Vn in this case, basically pretend this is EMF naught. Okay, it's going to be 10 volts. Okay, and then the resistor value and the capacitor values are these. Okay, let's see what happens. Okay, so we're going to calculate what Vc is. Right, Vc follow this equation, right? Omega times R divided by R squared plus 1 over omega square C squared. Okay. Okay. So up here we have 10 volts times the resistance value, which is 100 ohm. Right. All of this is in SI units, so we don't have to worry about unit conversions and stuff like that. Right. This is 100 ohm square. Plus, right, we need to convert this f into omega, so omega is actually just 2 pi times f. So 160 hertz times 6.28. I can sign into my phone. Okay, that should be about 1,000, right? 160 times 6.28. right? It's about 1,000, okay? This will be in radians per second, okay? Okay, this is 1,000, and there's a square there. And then the capacitor is 100 nanofarad, meaning 100 times 10 to the negative 9 farad, okay? Okay, all right. So up top we have about 1,000, right? This is going to be 10 to the 4, and 10 to the 3. Oops, so there's a square here also, right? All right, 10 to the 3 times 10 to the negative 19, negative 9 will give you 1 over 10 to 100 times 10 to the negative 6. Okay, and you flip this back upstairs, right? 10 to the 4 plus 100 times 10 to the 6, right? Did I do that right? I don't think I did that right. I'm pretty sure I did that wrong. Okay, let's multiply this number together first. This will be 100 times 10 to the minus 6 is 10 to the 4, right? 10 to the minus 4. Okay, this is 10 to the 4. Okay, okay. Notice that these two numbers are equal to each other, so you just get a factor of 2. Okay, times 10 to the 4, all square rooted. Okay, so you get 1,000. Square root of 2 is this 0.707 number that we just talked about. Square root of 10 to the 4 is 100. Okay, so this will be 10 volts divided by square root 2, or about 7.07 volts. Okay, okay, right. So that's how you pick a resistor and a capacitor value for a low pass filter. If you want to hear the low frequency sound, right? If you pick that value, instead of losing all of your sound, all your original voltage, you lose about 30% of it, but then all the high frequency noise goes away. Okay. With the 2 minutes we got remaining, I just want to show you guys the other version of it, right? Okay. So let's say instead of trying to pick up the voice of a person, right? You want to pick up like for example, your cell phone, right? It runs on about a 2.4 gigahertz band. So that's a high frequency, right? 2.4 gigahertz is a lot higher than 450 hertz, okay? The way you would do this is you basically just switch the position of the capacitor and resistor, right? And now instead of measuring the capacitor value, right, you measure the value that's coming out of your resistor instead, okay? And as we go up here and we look at this diagram once again, this little thing right here, right? When we're at high frequency, right, the resistor value, the resistor voltage is the one that has a big amplitude, right? So you're actually picking up the resistor value if you want the high frequency signal to pass, okay? And this is known as a high pass filter, and it's also what it sounds like, where if you have a high frequency signal, it'll allow it to pass through, okay? The example of this is that, like, let's say on your cell phone, right? Let's just try to draw a cell phone. The frequency of sound that comes, the frequency of electromagnetic radiation, the signal, basically, like, let's say your Wi-Fi or your cell phone signal, comes in, right, at about 2.4 gigahertz, means 10 to the 9 hertz, right? But there are other electrical signal around, such as these lights, right? These lights are going to be, this is the high frequency. You have a low frequency background, where it's like this is going to be 60 hertz or 120 hertz, or actually 180 hertz, right? These are much lower, okay? What happened is that if you pass the, so what happened is that when you just have a cell phone in a room, right, you're actually listening to both the high frequency and the low frequency at the same time, right? If you want to filter out the low frequency stuff, right, then you would put it through a high pass filter where you have the combination of the two coming in, you have it go through a capacitor and a resistor, but you only take the output at the resistor, right? Because the capacitor, right, is going to filter out, this combination of capacitor and resistor is going to filter out the low frequency sound, okay? And there's a couple of examples in the textbook that unfortunately I don't have time to go through, but that's how you would, that's how a lot of signal filtering happen right? You either put a low pass filter if you want to keep the low frequency stuff, and then if you want to keep the high frequency stuff, you put it through a high pass filter, where high pass filter is just the same circuit, you just switch the position of the two components, okay? So that's very useful, okay? All right, so that's all I have time for today. And so on Monday, we'll try to wrap up the chapter, and